having derived the integral form of momentum balance, looked at the significance of the terms there. We also looked at the how do you get the sign for the rate of momentum term, linear momentum term leaving. Let us look at applications of the integral momentum balance. Now, one common term or common variable which we are going to find out in all these examples is force. So, we keep talking about force, force, force in all the examples, that something is common to all the examples. So, what is the first example? You have a water jet, okay, and it impinges on a plate and you are holding this plate, and you have to give some force so that you can hold this plate. So, we are going to find out what is that force. And so, force to hold a plate struck by a water jet. Even without doing the example, we can say that this force required is to just balance the momentum. Okay. So, all these examples will deal with balance of force and momentum. So, that should be kept in mind. Now, this second example is once again a simple and a nice example. We have a tank and then there is water, but it is just not water, water is entering and then leaving, maybe we will take it this way. So, water is entering and then leaving, and this on a weighing balance, and I would like to know what is the reading shown by the balance, and the reading shown will include the weight of the water in it, the tank also, and of course, the momentum of the fluid, okay, and that is what we are going to see now. And the third example is so the second example is force due to weight and momentum inflow, that is a point we are going to discuss there. Third example is force required to hold an elbow. You have an elbow here which is a pipe joint. We use elbow to connect two pipes either same diameter or different diameter. In this case it is a reducing elbow. Why? Because the diameter is changing and there is a turn of direction as well. So, because of momentum, pressure, etc., this elbow will start moving if you do not support it. So, you need to support it. So, what is the force required to hold an elbow? And the fourth example, so all these are reaction forces. Remember we discussed about pressure force, the reaction force, frictional force. The last example is the example to illustrate frictional force. We have a pipe, flow through a pipe, and then we measure the pressure drop, temperature, pressure, etc., and find out what is the frictional force. From the pressure drop we find out what is the frictional force. Of course, other force which we came across was pressure, which we are going to come across at the boundaries, and of course, some examples will also include body force. So, these examples will include the momentum flow term and the forces, namely body force and surface forces. Okay, let us take the first example, and let us read the example. Water from a stationary nozzle strikes a flat plate, okay, a flat plate. The water leaves the nozzle at 15 meter per second, so high velocity. The nozzle area is given. Assuming the water is directed normal to the plate, okay, the water is directed normal to the plate. The reason is that if it is at angle, in reality it may be at an angle, but then you will have to take component of them. Okay. But now if you say it is exactly normal, then only that component along the normal acts. Suppose if it is inclined, a part of it will act on the plate, it makes the problem more complicated. That is why we say water is directed normal to the plate, and again once again after it hits it may get splashed, it may go at some other angle. We do not take all that, we say water nicely falls along this, rises along parallel to the plate. All these are simplifications done so that the analysis becomes simple, and then determine the horizontal force you need to resist to hold it in place. Okay. If you do not do this, suppose if you let us say water strikes this and goes somewhere here and here, then you should take some component of that along the x direction. But if I say water just goes parallel to the plate, falls down parallel, rises up parallel, then this there is no component of this along the x direction. This makes the problem much more simpler. Okay. So, we are asked to find out the horizontal force, which means we are interested in the momentum in the x direction, force in the x direction, etc. Okay. So, this one whatever I described is shown schematically here. the plate here and then our hand to support that, the nozzle, the water coming out of the nozzle, and these two show the direction in which water flows after hitting the plate. Now, the first step is to select the control volume and represent the forces. Okay. Now, the control volume what we have selected is shown here. When you look at the control volume, there is a momentum flow which crosses the control volume, and then there is a force of our hand on the control volume which is also included, which acts on the part of the control surface. So, when you choose a control volume, you should make sure that whatever we are interested in acts or crosses the control volume or control surface. In this case, this flow crosses the control surface and this force acts on the control surface. Now, the control volume is so chosen that this area and this area are same. I am focusing only on the x direction. Okay. So, let us look at it. Control volume, area of the left face, left surface equal to area of right surface. So, that we will come to that shortly. Okay. Now, all the forces are shown here, all the forces are shown here. Let us look at what are the forces. First is the atmospheric pressure, okay. Force exerted by atmospheric pressure, and we have seen discussed that pressure is always compressive and acts into the control volume. That is why the direction of pressure is shown to the right here towards the positive x axis, and here it is shown towards the left towards the negative x axis, and we have shown a uniform pressure across the entire area, and just the effect of pressure will just cancel out each other. This, the force due to this pressure is P atmosphere into A, and this also is P atmosphere into A, and that is why we said area of left surface is equal to area of right surface. That is the implication of that statement. If you do not do that, the force due to pressure will not cancel each other. The force magnitudes are same, the directions are opposite, they just cancel each other because of atmospheric pressure. Okay. Now, what are the other forces shown? Of course, the weight is shown, which is not of significance to us because we are going to do a balance in the x direction. The force due to weight acts in the along the y direction, but anyway shown here for completeness. Now, when we have this plate and apply a force, force is exerted by the hand on the control volume. Okay. I think that is very important because that changes the sign, and this force is called as reaction force. Components of reaction force of hand on control volume. So, those every letter, every word there matters. Force exerted by our hand on the control volume. Now, it could be at any angle, that is why we split into two components, R x and R y. The x component is R x, the y component R y. Now, to begin with, we will not know what is the correct direction. So, by convention we take R x and R y to be positive along the x and y axis. Eventually, we may find out that it is negative, which then we will say we have to exert force in the opposite direction. But to begin with, and analyzing any example, we take the direction to be positive along the x axis and y axis. So, R x and R y are components of reaction force of hand on control volume, and then R x and R y are assumed positive along the positive axis. End result may not be same, it may be negative, we will have to interpret differently. Okay. And force of what is the force of control volume on hand? We use Newton's third law, and it is so negative of R x and negative of R y. That is why I said reaction force of our hand on the control volume, that terminology is very important, because if it is force of control volume on hand, whatever control volume exerts on our hand is negative of what we are exerting. So, it is minus R x and minus R y, okay. And which we have discussed, atmospheric pressure acts on all surface of the control volume. I mentioned about the effect of pressure, atmospheric pressure on the left and right surface, but of course, pressure acts on these two top and bottom surfaces, but we are not interested in that because that is in the y direction. Okay. So, what we have seen here is the control volume, selection of control volume, how do we select, and what we have seen here the right side diagram are what are the forces acting. If this picture is very clear, it will become easy for us to write the integral balance equation. Okay. Okay. Now, if you look at this diagram on the right, I have shown uniform pressure throughout. Now, for that we should, of course, the pressure here everywhere is atmospheric, pressure here everywhere is atmospheric, that is very obvious. Now, what is the pressure across the cross section, across the surface area where there is flow? For that we should use the physical fact that pressure in a free jet is atmospheric. What is a free jet? You have a nozzle and water just flows out of the nozzle as a free jet. So, pressure in the inside the fluid region is atmospheric if it is a free jet. If you are not stating this, then I cannot show atmospheric pressure for this part of the surface, because it will be some other pressure. Only if you assume that the pressure in a, that is what is that, this area, the pressure in this area is also atmospheric, only then I can show uniform pressure throughout. If it were not atmospheric, here on let us say slightly higher pressure, the pressure will be different. Okay. That is only based on that assumption I can draw a uniform atmospheric pressure throughout. Okay. Let us write the integral linear momentum balance equation in the x direction. In this example, we are doing a balance along the x direction. Okay, that is the rate of change of x momentum with respect to time, net rate of flow of x momentum out through the control surface, body force acting in the x direction, surface force acting in the x direction. Now, of course, a steady state problem. So, the first term goes off leaving with the second term and the forces on the right side. Now, let us first take the rate of momentum term, okay, rate of momentum term. Now, in this control surface only at section 1 there is inflow, no other part of the control surface there is flow in the x direction. Here there is you do have flow here. So, you do have rate of momentum leaving in etcetera, but that is in the y direction, because we are writing a balance along the x direction. The only part of the control surface where you have flow in x direction is only this part of the control surface. Okay. So, all others are 0. So, that is why I replace control surface with control surface 1, that is part of the that part of the control surface where the free jet enters. Now, let us simplify this expression, this integral expression. Now, we assume the uniform flow. What does it mean? As usual, there is no change in velocity in a direction perpendicular to the flow. We have uniform velocity, which means that I can take out the entire term outside. Of course, I also assume density is uniform. Let me show the next step and then explain. Okay. So, the integral expression is rho v x v dot n dA. Now, because I am assuming all these to be constant, I take out. So, integral dA becomes A, because it is section y, I denote it as A1. Okay. Now, the density term is written as such. Now, what is the velocity Vx? Vx is along the positive x axis. So, Vx is equal to V1. V1 is the magnitude. Look at the representation here. V1 is the magnitude of velocity, 2 meters, 3 meters, whatever meters per second, in this case 15 meter per second. When you write as a vector, the velocity vector V as x component Vx and of course, along the I direction. In this case, Vx is equal to V1. Suppose if it were along the negative x axis, it would be minus V1. In this case, it is just V1. Okay, now, let us substitute here. For Vx, I substitute V1. For velocity vector V, I substitute V1 I. V vector is written as V1 I, because it is along the positive x axis, and then dotted with, there is a dot here, dotted with what is the n vector? Remember, n is always outside the control volume. So, n vector is in the negative x direction. So, I substitute minus I for n. So, now let us simplify this. I have a negative sign here, the density term here, V 1 into V 1 gives you V 1 squared, and then I dot I is just unity, and then I have A 1 here. Okay. So, we have to be little careful in arriving at the correct, especially the sign of this particular term. If you recall back our earlier discussion on the combination of two terms resulting in a sign, we can quickly check this sign. V x is positive, okay. V dot n is negative because it is inflow resulting in a negative sign. Okay. We said these two signs together constitute give the sign for the entire term. So, in this case one is positive, other is negative, resulting in a negative sign. Okay. So, this, and that is why we did not discuss much on simplification of integral balance earlier. No way we can discuss all this in a general way. So, we discuss for a specific problem. Okay. So, I like to repeat this one because later on I can quickly go through this step. What we have is rho V x V dot n. V x in this case is the component of the velocity in the x direction, which is V 1 being positive, and I substitute for V x. Then for V vector I substitute as V 1 I along with the direction vector, and for n I substitute as minus I because it is along the negative x axis, the unit normal, and simplifying we get minus rho V 1 squared A 1. Okay. So, we have written the integral form of the momentum balance, the net flow momentum rate of momentum flow term, and the forces. Okay. So far we have discussed only the rate of momentum term. Okay. Now we have discussed the forces on the right hand side. Since we are doing balance along the x direction, momentum balance along the x direction, there is no body force. The only body force you are considering is the gravity, that does not act along the x direction, it acts along the y direction only. Now, what are the surface forces? How do we account for them? Okay. Surface forces are due to atmospheric pressure, of course it cancels out, and due to our hand, the reaction force because of our hand. Now, focus on this diagram where we have shown all the forces. So, force due to atmospheric pressure is P atmospheric into A, and remember it is the into the control volume, that is why it is plus P atmospheric into A, and on the right hand side it is once again P atmospheric into A, but it is against the positive x axis, it is along the negative x axis. So, because it is into the control volume, and that is why you have minus. See, all of, when I say force, it is positive when it is acting along the positive x axis, and this force acting along the negative x axis, and that is why we have minus P atmospheric into A. Now, what is the direction of our reaction force? We have assumed it to be positive along positive x axis, and that is why this also plus R x. These two terms cancel out, resulting in R x. So, as far as the forces are concerned, there is no body force. The only surface force remaining is that due to the x component of the reaction force exerted by our hand on the control volume. Okay, now let us substitute all the terms in the integral balance equation. The rate of momentum term we found out to be minus rho V 1 squared A 1, body force 0, surface force R x. So, let us substitute. Where are we substituting? In this equation we are substituting in the integral balance equation. Becomes very simple now, minus rho V 1 squared A 1 is equal to R x. Okay. The way in which I have substituted is that the rate of the convection term, let us use the word convection term, the convection term is on the left hand side and the force term is on the right hand side. So, by convention the convection term is always on the left hand side. Okay. The unsteady state term is also on the left hand side, but we do not have unsteady state term. So, by convention we have written the convection term on the left hand side, force on the right hand side, but now as I told you, the key physical variable of interest in all the integral balance equation, the force. So, I take the to the left hand side R x and bring the convection term to the right side. Okay. So, you may wonder why write here minus R rho V 1 squared A 1 equal to R x, on the next step write R x equal to this. What we want is on the left hand side but as per the conservation equation the force is on the right hand side. So, please keep this in mind. Some books may straight away write this expression, but we are trying to be more consistent. Okay. Now, just substitute rho is thousands of water jet of water, velocity was 15 meters per second, the area was 0.01, giving us a minus 2.25 kilonewton. Okay. To begin with, we said the x component of force acts along the positive x axis, but now we have a plate, even by intuition we can feel we have water jet hitting on it and we are applying a reaction force. So, our force should be directed towards the negative x axis, that is the result we have obtained. We apply a force, our force on the control volume should be towards the negative x axis, but what did we say, r x is towards the positive x axis, that is why we resulted in we have got a negative sign for r x. Okay, so, that is what the negative sign implies. So, horizontal force, or to be more precise, the horizontal component of the force of our hand on the control volume, every word here is important, of our hand on the control volume is equal to minus 2.25, which means that it acts towards the left. Every time it is also good to check with our physical intuition also, sometimes we may get confused the negative or positive sign. Okay. And now, what is the horizontal force of the control volume on the hand? It is negative of this plus 2.25. Of course, we are interested in this, the first minus 2.25, just for understanding. Of course, it acts to the right. So, control volume exerts a force on the hand to the right, and we have to exert a force to balance that towards the left. Okay. So, the force generated is entirely due to the momentum. Okay. The force, we have to balance the momentum with our force, okay, and the x component, and of course, horizontal momentum.